Greeting teacher. Here is the final project of electric traction and rolling stock technology. Our group interested in the nose of the train. So the content will include objectives, related theories, introduction, modern dimensions, simulations, results, and discussion. Why do we care about the nose of the train? Well, first is for its appearance, and secondly is for its performance. In performance, we care how to make it goes faster and how to reduce the energy consumption rate. If we take a look at the figure, the reason why the shape of the leading part is changed between car number 1 and car number 10 for alpha X is to analyze the difference in pressure and air resistance of the car body when entering the tunnel and to develop more optimal shape. Here is the related theory to the nose shape of the high-speed train. Biomimetic scaling of noise reduction. It means that is the mimic chemical process that make it related to uh, the bird nose shape. So Kingfisher's beak was transferred into the design of the high-speed trains. These trains became quieter and more efficient, require 15% less energy, while traveling even faster than before. Let's take a look at the figure A and B here. B is the kingfisher's beak that generates no vibration in vertical diction, but A generates a lot of vibration. As a result, the fish is activated to escape. So the nose of the train can generate noise, and most of the people don't like it. So engineer would design something that similar to the kingfisher's beak or the nose to reduce the noise. Let's dive in more technical theory, shall we? Fluid dynamic. Wake flow. The wake is the region of disturbed flow, often turbulent, downstream of the solid body, moving through a fluid, caused by the flow of the fluid around the body. So that generate the drag force. So why we care about this? Well, because if we can reduce the drag force, that means we can go faster and we can reduce the energy consumption rate as well. Here's the aerodynamic force diagram. So the airfoil acts as the train moving forward to the left, and the flow direction of the fluid is to the right. And that generates lift, which is pointing off, and the drag, that opposite direction of the motion of the train. And that we can get the total aerodynamic force, which is the combined vector between lift and drag. So the engineer has to consider about the aerodynamic force in designing the train and the nose of the train. So next we will see the introduction.
Okay, for this slide, we want to show an introduction about the four classic node train shafts. We need to show you guys about the four type for the node train shafts in this picture. In the picture one, it shows the billet shaft. In the second one, it shows the fin shaft, wedge shaft, and the last one we want to show the inverted buttock shafts. Thought of them is related about the velocity, the pressure and coefficient of pressure and the drag force that react with the air force in the air, the force in the air, or aerodynamics when they drive the train. Yeah, and lot of them used to develop by the times and in the past until now. And each of and lot of them is the different type of the node train shaft in different country that we need to study and learn about it because it is so much important about the speed of the train. And could you guys tell us which of these shapes produce the less drag force? For this slide, we show the type 1 of the node train shapes is billet node shapes. We can explain you guys to show in the past of the billet node shapes is the J3A Hudson Stream locomotive, which was decided by Henry First, if I can read it correctly. For the J3A was built in the 1933 years. A prototype two-car set decided to run between Berlin and Hamburg at an average speed around 124 km per hour. It's faster than any other train at that time. We can show you guys in next slide in the figure 2. When we compare with the Mercury, the design was visually resistant, giving latent hints of the power available from the 12 cylinders Maybank diesel engines. One at neither end, like the Rumble automobile of 1921, and the whole was encased in a smooth envelope with a vertical emphasis like a shark's fin or a submarine conning tower. And other picture is the models billet node shapes is and A5 really show off its extra long nose at Tokyo Station. Yeah, for the Tokyo station, there are the A5 train, or other name is the H5. The H5 is the high-speed train in modern times in Japanese. There are the speed around 300 to 320 km per hour is a high-speed train in Tokyo. For the second type of the node train shapes is with node shapes. We can show you guys in the figure 2 for the example of the train in the past. The Hamburg Fire West shaft was Germany's first fast diesel train and is credited with attributing the fastest regular railway connection in the world in its time. For the other picture, it shows the Vanderbarans trains in India Railway is the high-speed train in modern time. There are the speed around 130 to 150 km per hour. It shows the shape of the nose in the past and in the modern of the west node shapes. For the third type of node train shapes is fin node shapes. We can show you guys in the figure 3. Sonico Gateway A4 stream locomotive, the battle. The cipher diesel which was built for the Chicago, Burlington, and Quincy railroads in 1934. It was an advanced vehicle for its time, having a body shield built up from stainless steel sheet, support built like an automobile, to form a comparatively lightweight but rigid structure, like on U.S. locals. The cipher was given a skirt to protect the leading bogie from impact should an animal stay onto the track. Here, the skirt and the driver's wheel shield were integrated into the nose, so that together they formed a simple convex profiles. For the first type of the node train is inverted bathtub node shape. We can show you guys in the finger for the phaser train. It's quite similar with the third type, fin nose shapes. I will explain you more about the phaser train in the California. In the California, there are the California phaser. It's a passenger train operated by the EMA between Chicago and the San Francisco Bay Area via Omaha, Denver, and Salt Lake City. At 2,438 miles or around 3,924 kilometers. It is Amtrak's longest daily route and second longest overall after the Texas Anchor Drive Weekly continuations from San Antonio to Los Angeles, with tower times between the terminals taking approximately around 51 or 52 hours. For this slide, we show the model node train and node length of the train. In the model node train, we use in the first type the bullet node train. The bullet node train in the wrinkle in the slide, we show the Alpha X, Japan's next generation bullet train. The Alpha X test train is the next generation of the Shinkansen train. It's seen at the JR Morioka stations. It's used on the May 16, 2019 in the Japan in the high-speed train. It's the model nose train that we use in nowadays.
Modern nose train and nose line. As the figure shown here, we can see that the nose line of the train has the effect of the speed of the train. For example, if we look in the Austria, it can travel 275 km per hour, and the nose length is relatively small if we look and compare to Japanese train. It can travel up to 600 and has greater length of nose. This slide shows the Japanese E5 series Shinkansen train. As we can see from the figure, bottom to the top, the first model of E5 series has shorter nose train, the second one has a little bit longer nose train, the third one is the inverted bar tube shape and has longer nose train, and the fourth one has greater nose train in length, and the next one is kind of the bullet train, has longer nose train, and the next one has the combination of the nose train of the bullet point and the wedge. Until the last model, it has greater rank in nose train and it has the combination of bullet and wedge, which can achieve greater velocity. Let's talk about simulation for 4 different types of nose train. We design 4 different types of nose train and simulate to find out which of these 4 has the smallest value in terms of drag coefficient. According to the simulation result and the formula given, we find out that the bullet shape has the minimum value of drag coefficient and the second one is wedge. These two shows us that they has relatively small drag coefficient compared to fin and inverted bar tube. We are still at the study of simulation for 4 different train nodes. In this slide, we add to both ends of the model to be as similar as possible to the real nose train. According to the simulation, we can conclude that bullet shape has the smallest value in terms of drag coefficient, and bench also has a very small value compared to fin and inverted bath tube. From the previous slides, we can conclude both studies in the table as shown in the slide here. We can see that the bullet shape has the minimum value of drag coefficient compared to bench, fin, and inverted tube. However, we still can see that bench has also the small value in terms of drag coefficient compared to fin and inverted bath tube. So for the design of the nose train in the modern technology, they combine bullet and wrench to the same nose train, as presented in the early slides for Alpha X is the combination of bullet and wrench. This figure is adopted from a research study about the train travel in the tunnel with different nose length, 4 meter, 7 meter, 9 meter, and 12 meter nose length. These figures are the results of the simulation for different nose length 4, 7, 9, and 12 meter. According to the simulation, figure B, we can tell that the velocity for the nose length of 12 meter has greatest velocity compared to the rest.